Hi guys, so in this video lecture we'll be continuing on um, practicing on some examples on the ozone analysis, and then we'll be moving on to our next topics, which is called selective ozone analysis and Wurtz reaction. So okay, let me start off with the examples. If we have this and this, so what would happen? So this is just a benzene ring, and as you know that it would have one more structure in which double bond will not be present between two CH3 groups. So in both the cases ozone lysis will be taking place. So we are drawing all the possible structures of the ozone lysis. So one would be uh, uh, so, these will be twice in number plus this one, and this would also be twice in number. Okay, and for this we can say that if we break down this, we will have something like this and this. Similarly, would be having one more structure like, or two more structure like. If we break this, then we would have something like again this. Okay, and if we break this, we would have this. Oh, actually I drew already this structure, so we need not draw this structure again. So this would also be twice in number. Why? One because of this and another because of this. Okay, so these are the structures will be formed. Okay, let's look at okay, if we have this a reagent, a substrate, and on ozone analysis we are getting this as the product. Then what is A? And so A would be we easily know that this has to be a pi bond. There has to be a pi bond when we actually remove this. So the structure should be if I guess, the structure should be something like this. Okay, because ozone analysis of this structure would give me these products. Okay, so let us take example, look at third example. We have this product on ozone analysis. This gives me this and this. So obviously B structure will be something like this. Okay, let us look into the fourth example. We have a product C on ozone analysis in presence of zinc. We have something like this. So what would be C? So C would be easily, we can say that C would be something like this. Okay, so with this we come to the end of simple ozone analysis, and let's have a look at selective ozone analysis. Ozonolysis. Okay, so in selective ozone analysis, suppose we have this as our substrate. Then on ozone analysis we make the arrangement in such a way that the ozone lysis occurs only on this pi bond and not on this phenyl ring. Okay, so two compounds A and B are formed. So those two compounds can be easily identified, as one of the compounds would be this aldehyde and another would be this one. Okay, so this completes our ozone lysis and selective ozone lysis part. So let us start with Wurtz reaction. Wurtz reaction. So when alkyl halide reacts with sodium diether alkane, sodium diether, then alkane will form, and it is known as Wurtz reaction. So let me write it for more clarity. So when alkyl halide reacts with sodium diether, alkanes will form. Alkyls will form, and it is known as Wurtz reaction. Okay, so let us understand it by taking an example. So this is an alkyl halide. Okay, and in presence of sodium diether, it will actually combine to form this alkane. Okay, and what is the mechanism going behind the scenes? So let us write the mechanism. Mechanism is, we have first sodium in presence. Okay, so sodium in presence of dry ether will look something like this is sodium ion and this is dry ether. Sodium will break up into sodium plus electron, sodium ion plus electron. Again, because it is having lone pair of electrons, it will be combining. Oh, not a complete bond. Okay, so this would be how sodium would be placed in dry ether. So what would happen is the released electron, the released electron will actually attack the ET and the Br free radical, and the ET free radical would be formed. And now these two ET free radicals actually combine with each other to form butane. Okay, hence we get our product as butane. So let us look at some of the examples of Wurtz reaction. So we have CS3Br plus ETBr in presence of sodium dry ether. So what will happen? What would be the free radicals formed in the intermediate? Free radicals formed would be this and this. Now we have two free radicals, so two free radicals can combine either with this one. So either this can combine with this or this. So we have total 2 into 2, 4 products formation would be there. So they would be like when CS3 combines, when ET combines, and when actually not 4, we will have 4 products and they would be like this, but CS3 and ET are the same, so we have twice CS3 ET. Okay, so total 3 products would only be formed, and the 4 type of crossing would be there, 4 crossings and 3 products. Okay, so let us look at some of the notes here. Notes would be that methane cannot be prepared by this method. Why? Because this is a addition reaction of two free radicals. So methane CH4 cannot be formed because it is containing only one carbon. So odd number of carbon atoms means one number of carbon atom cannot be formed from this reaction. So the minimum number of carbon atoms that would be there in the principal carbon chain would be 2. Okay, so let me write all the notes point wise. Methane cannot be prepared by this method. Okay, second point would be when two different alkyl halides are used, three products will obtain. When two different alkyl halides are used, then three products will be obtained. Okay, the third point is normal alkane having even number of carbon will be obtained in high yield of reaction, and alkane having odd number of carbon will be obtained by low yield in this reaction. So third point is normal alkane having even number of carbon atoms will be obtained in high yield. And similarly, alkane having alkanes having odd number of carbon atoms will be obtained in low yield. Okay, so let us do some more practice on the product formation of Wurtz reaction. So here to tell the products formed when we are using CS3Br and reacting it with sodium triether. The product form would be simply ethane. What about this? In presence of triether, we would have this. Okay, the third example is, what if we have we would have like this. Okay, so and let's make this third example more interesting. What would happen if we have something like Br and this and the presence of anhydride? We would have these products. In this case, we will be having only four member chain, not 5. Okay, and the third one will be okay. Yeah, these are 2 carbons, so 4 carbon here. In this we have 3 carbons, so 1 2 3 4 5 6 carbons here, and one would be 5 carbon chain. Okay, so let us take some more examples. So what would be the product in this case? So this reaction will have a very low yield because free radical on the double bond is less likely preferred, so it's still we would have some reaction going the forward direction, but the reactions yield would be very very low, right? Okay, but if in this case we are here, then it would be a very good yield. We would have something like this. Okay, so but if you look closely on this on this substrate, you will find that we have a carbon 14 isotope here. So what will happen in intermediate is, this is our intermediate I am drawing. We have a free radical here, okay, and we have a double bond. We have a double bond here and a carbon 14 isotope here. So one free radical would be here, or it can actually do a hyperconjugation, free radical double bond hyperconjugation to form a double bond here, and the 14 carbon will have a free radical here. So these are the intermediate formed. This sign is I am showing for intermediate products. So what would be the total number of products? We will have 3 products, and those 3 products will be, one would be this only, okay, another would be between these two, and third will be between only this. So I hope you are able to draw the products, not a big deal. So what if I have A plus B as substrates, and we have sodium triether, so we know that it is producing an hexane. So obviously A and B would be this. Okay, so with this we come to the end of this video lecture. In the next video lecture we'll be seeing addition reaction of alkenes, Markovnikov rule, anti-Markovnikov rule. Okay, so till then, good luck and goodbye.